And hopefully we won't have any technical problems this time, but at least you're all here. Almost all of you are here. Bioeffects, this is what we call anything that causes troubles to the body potentially. And of course, ultrasound of all the modalities is probably about the least concerning for bioeffects, but we do have to be concerned about it. And the FDA, still can't think of what FDA stands for. I'm so embarrassed by that. But FDA regulates us pretty closely, and some of the tools that they use, both researchers and the government use to test our equipment is we're going to talk about. So the first one is a hydrophone. I actually had a class. I used to teach ultrasound years and years ago, and I had a class build a hydrophone. That was actually when Radio Shacks were still around. It was kind of cool. We built this hydrophone. We actually had a little piezoelectric submersible material, and we took it to a lake and put it underwater and just dropped rocks in the lake. I don't know. We had to do it. We had to do something, right? So that's what we did for our little project there. So they're pretty simple. Little piezoelectric material. So if we're looking at this picture here, we have this little pencil-like structure here that they could hold on to. They could clamp into place, and the red box there, the salmon-colored box, is a piezoelectric. So just like the piezoelectric that we use to create sound and listen to sound, this piezoelectric material is used to listen to sound. Of course, this hydrophone could be placed, well, where it is, somewhere looks like the focal point. It could be placed up here in the near zone. It could be placed in the far zone. Kind of getting different ideas of what kind of power and intensity we're seeing. I could actually even put it slightly off to the side and see the difference between kind of the edge of the beam versus the right dead center on the beam. That's connected to an oscilloscope, but kind of an oscilloscope is a little bit similar to our waveform. Well, I don't want to say waveform because that's blood, but the oscilloscope is, it can read very precisely what's going on. And not only does it look at the overall intensity via really a pressure intensity, which that pressure, basically sound is pressure, right? That sound pressure hits the piezoelectric material, creates a voltage. Here, let's put a little E right here. So electrons are sent back through the wire to the oscilloscope, and just like with our equipment, I'm sure there is an amplifier and everything in there. And it could tell the overall strength. It could also see the pulse repetition period and frequency pretty clearly because, well, and not to mention the pulse duration. And so actually, if I drew a little more accurate little guy in here, it might be seeing something like this. Connected by a line there. It actually reads. It's fast enough, of course, to read the pulse repetition frequency and even figure out what the pulse duration is. So that's the hydrophone. Oh, and there's also a disc type hydrophone, which would look like it would lay at the bottom. Probably we would have like a jar filled with water, and you lay that at the bottom, and this really does the same thing. PRP, PRF, PD, all the same things. Here, let's draw a little better. There we go. So either way, pencil type, disc type, they're really the same type of thing. The next one we could talk about is the radiation force. Mandalorian's on, by the way. First episode was really awesome. Second season. Anyway, radiation force. We could use a feedback microbalance. And it's a balance. It really is. It literally feels pressure. So a little bit different than an piezoelectric element, which feels pressure but creates an electric charge. This one literally feels the weight of the pressure. And you guys remember, I'm not repeating, I feel like I'm repeating myself because I know I recorded all this, but you guys didn't see this, right? Tell me if you did. I'm getting very confused in my old age. Anyway, when we did at the beginning of the semester, we had our little Tupperware out, and let's just draw a Tupperware right here. A little bit of water in there, and we could actually see as the candy started to dissolve, starting little flakes of sugar and plastics or whatever else is in candy started floating around, these little things. And then when they get into the beam, they started going down very quickly. And then they'd even sometimes be pushed off to the side from that beam. That's a physical force. It's a physical weight that can be actually measured. So it's a feedback microbalance. And I drew this the other day when I was recording. It actually reminds me, and for the love of God, I could not find this on this. I couldn't find the right keywords to describe this and find what these things are called. But you've probably seen them in like a science classroom or something where you have a little evacuated bell, glass bell, so vacuum bell, with this balanced thing in the middle, and it's like these little paddles, and when sunlight hits, oh, these are actually, there are toys that you could put on. I know it's a little bit different. They use solar power. But this doesn't use solar power like a solar panel, but light is shown upon this, and literally the photons, the energy of the photons, well, heats up and spins this this guy around. It kind of reminds me of that. It's just something as weak and as a flashlight could actually make this thing spin. So very precise equipment. This has absolutely nothing to do with what we're talking about, but I thought it was an interesting analogy. All right, so the radiation force can be measured with a feedback microbalance. We saw Schlieren when we did that, when we looked at that single pulse of ultrasound. There was a video of a single pulse of ultrasound. It went down and then it bounced this way and bounced back that way. And it was kind of cool. It was one of your assignments just to watch it. That was Schlieren optics. Schlieren optics are really amazing. They could see things that would normally be invisible. And here we have a transducer here, creating a sound wave that's bouncing off of this mirror. You could actually see these guys bouncing in such way. Now, this is probably ultrasound, but it is not imaging ultrasound. Imaging ultrasound, the wave fronts would be so much closer together. Not to mention imaging ultrasound does not travel through air very well at all. So I think this is ultrasound. This is higher than what we could hear, but much lower than imaging. That doesn't really matter. But this is acousto-optics. This is just a fun experiment showing, it's not a real FDA experiment, but acousto-optics, as in like the Schlieren imaging that I showed you, that video, that can be used to evaluate the beam characteristics. Not much on acousto-optics. The chances of you being asked that on an SPI are close to 0. Now, you might be asked something, and it would be like one question. It wouldn't be a ton of questions, but it might be asked, you know, what might be used to determine the total power of a ultrasound beam or the total heat output of an ultrasound beam, and you would put a check mark next to calorimeter. So a calorimeter is basically a little thermometer, and if you put a ultrasound beam onto a calorimeter for X amount of time, maybe they have precisely 20 minutes, and exactly at 20 minutes they look at the temperature and say, ah, it raised the temperature by 2 degrees. That might be a little bit dangerous. Let's lower the, the FDA might be saying, yeah, that's pushing our luck. Let's reduce the power for this particular ultrasound unit, something like that. So calorimeter is really just that, just a thermometer that tests how much you've heated up a test object of some sort. I think the book says it's like a thermos. You heat up a thermos. I don't think a thermos is a good example because you pour stuff into a thermos. But anyway, thermocoupler, same difference. This is a thermocoupler is a thermometer. It's just not a traditional thermometer. It actually uses 2 different wires. Here I have, inside of this beam of sound, we have 2 different wires. I'm sorry, 1 wire made of 2 different metals. That's what I really should say. A blue metal and a pink metal. Of course, they're going to be boys and girls. But these 2 metals, as they heat up or cool down, you know, as they change temperature, they have different characteristics as far as how electrons flow through them. And by looking at these characteristics carefully, they can get very accurate temperatures in very tiny places. So a thermocoupler can be placed inside the beam. Once again, this looks like it's around at the focal point of this beam, and we're able to tell how much heating up is being produced. So once again, you put it there, 10 minutes, 20 minutes, 50 hours, whatever it takes to figure out what kind of temperature changes we can expect. So that's a thermocoupler. And then, dude, crystals, man. Crystals are the answer. Now, I don't have a picture for this other than a stupid quick crystal that I created, but literally like a mood ring type crystal where it doesn't really tell your mood, but people thinks it does. And these stress control biofeedback cards they have here on page 404, where it's just really just telling the temperature. And of course, if you have a crystal like that, let's actually do something. That's not what I want. Oh. Let's do this. And then on that, we have some kind of and the beam comes down and hits, actually, let's make this beam even smaller. And then you see your crystal change color here every time. Crystal changes color. We not only get a color change, which kind of gives us an idea of the amount of energy because of the temperature. Different colors will be different temperatures. Here we'll make it really hot now. We're going to cook our way through there. But also we actually get a kind of an idea of beam diameter and beam shape from using one of these. I'm sure it's a little more technically sophisticated than the picture on page 404. All right, well, that's some of the tools that researchers, manufacturers, the FDA uses to test all this stuff. And of course, we have a little section on risk and benefit. This is kind of like, it's close to Alara. Sorry, my screen was moving back and forth while I'm trying to write here. Alara, as low as reasonably achievable. Almost forgot that one. In risk and benefit, is the risk of doing an ultrasound worth the benefits? Well, 99.999999 times out of 100, yes. For ultrasound, the risks are extremely low. I've had students, I could tell you, who were pregnant and did not want to be scanned because they didn't, even though they were going to be ultrasound technologists and believed in ultrasound, they also were concerned about their baby and they didn't want to be scanned. They also probably thought it was icky to have their classmates scan them too, I guess. But I've had doctors refuse to let let their patients come to us for practice scanning because the doctor says the risk does not outweigh the benefit, which I disagree with because the benefit would be producing competent sonographers. So if he wants incompetent sonographers, then he's right. So the risks and benefits. So extremely high ultrasound intensities, of course, can damage tissues, but we don't use extremely high. Dosimetry is basically the science or the study of identifying and measuring the characteristics, in our case, of ultrasound and the biological effects that it can create. X-ray techs have to wear a dosimeter. I think it's called a dosimeter. This is Max, and he's in trouble because it's actually glowing. There's so much X-ray around it. But X-ray techs have to wear these all the time while they're working to get an idea of how many X-rays that they are absorbing throughout the day, throughout the week, month, and year. Ultrasound techs do not wear these, but of course, when it comes to X-ray, CT, nuclear med, we do need to be cautious of that. In MR, we have to be cautious of other things, like bringing something metallic into the MR and being drawn into the machine. Okay, so dosimetry is just the study of doses. One of the things that we do in dosimetry is in vivo, which, if you speak Spanish, should make some sense to you. It's the literally in the living. Literally meaning in the living. So in the living, studies are not generally done, well, retrospective studies on patients can be done, but laboratory studies are done on mice embryos, just just living tissue in general, they could hit with an ultrasound beam. And generally, you might hold down a mouse embryo for a very long amount of time and hold the beam above that and see what kind of effects you could have over time. So you can go in vivo, you can go well beyond what would normally be expected just to see, the end result of something like that. In vitro is in glass. And so it looks like I put a little embryo inside this glass, and I shouldn't put embryo inside the glass because that would be literally in vivo. But in vitro would be, actually, the book even says a computer model estimating the temperature elevation of tissues is actually in vitro research. Or if you're doing, a thermocoupler or a calorimeter, that's kind of in vivo research. You're not using a real living tissue or mouse. So of course, the challenge for in vitro is to relate in vitro results to the clinical setting, but you generally can. AI, so there's some statements in here. I do suggest you read the whole chapter. I'm not giving you everything in the chapter, but AIUM, American Institute of Ultrasound in Medicine, in vitro bioeffects is important. In vitro bioeffects are real, even though they might not apply directly to a clinical setting. And each in vitro bioeffects research claims that direct clinical significance without in vivo validation should be viewed with caution. So just because you can raise a temperature in vitro to 4 degrees higher than normal doesn't mean that's going to happen in vivo inside the body. So there does have to be a correlation between the two. They complement each other. Now, next thing we talk about is the mechanistic approach versus empirical approach. And I had a little time this morning to look it up on Google. I Googled these as well, and we don't really get a lot of definition, but a mechanistic could be a cause and effect. Take a guess at the mechanism of punching someone in the face, and let's figure out what the effect is. So we come in, we punch a bunch of people in the face, and we see what the effect is. Or in ultrasound, we come in with very high doses of ultrasound, or let's say really long pulses of ultrasound, Doppler pulses of ultrasound over a period of time. Let's see what the effect is. And so it's kind of figuring out mechanically what is going on. Proposal that a specific mechanism has a potential to produce a bioeffect. So I'm guessing punching you might hurt. On the other hand, the empirical approach looks at exposure and response, seeing the effect and more or less working backwards. So the empirical approach is based on the acquisition and review of information. I think it's a little more closer to epidemiology, where you take a population that probably maybe already was exposed to ultrasound in utero, and we look at them, in reverse and see, all right, 1% of these people were hard of hearing, and was that caused by ultrasound? Let's go backwards and look at that. So seeing the effect and kind of working backwards from there. Not a big SPI question. If it were, they would give us more to work with. thermal mechanisms and cavitational mechanisms would be a little bit more. So let's look at our thermal mechanisms here. So the TI, just in general, is thermal index, and that's obviously how much we're heating it up, how much we're heating over time. Core temperature is normally, I don't know what frogs' core temperature are, they're kind of cold-blooded, but 37 degrees Celsius, of course, not Fahrenheit. So we have several different ways of measuring that, and the machine and the engineers and the researchers and the FDA, they all get together to work out what they know to be true to the best of their knowledge, what they know to be true. So we have thermal index soft, so soft tissue. So that's TIS, and if you ever see that on your screen, that's what it means. It's and by the way, you might have a TIS indicator for a carotid exam, but a TIB indicator for a OB exam. So you might have different ones there. The more important of, well, these last two, this one, TIB and TIC, thermal index bone and thermal index cranial, which is also bone, of course. Bone absorbs a lot more ultrasound energy than tissue does. Therefore, it heats up a lot more, and the tissue surrounding that bone is in more danger. So when we're talking about a fetus who's just starting to develop calcifications in their bone, those calcifications will warm up faster, and so that is a concern, especially in the cranial. So I know the TIB for bone currently is less than or equal to 1.0. And I read something today where they're looking at trying to lower that to less than 1.0, but I don't know. Um, 2 to 4 degree rise in testicular temperature can cause infertility. So tissue heating is important. Although if you think about it, you know, we have fevers, we stand out in the sun, we get in hot tubs. Our bodies can handle a little bit of extra heating, but as always, fetuses, embryos, a little more at risk. The number one for heating, the number one intensity ratio for heating, spatial peak, temporal average. The limit there is 720 milliwatts per centimeter squared. So that's milliwatts per centimeter squared. That must be an intensity, right? It's not an overall power. Well, power has something to do with it, obviously, but it's the intensity that researchers and bioethicists are most concerned with, is the intensity of that power. If that power is spread out over a longer period of time, lower intensity, it's not going to cause problems. Or if that power is spread out over larger area, lower intensity, not a big problem. Oh, and temperature, spatial peak temporal average increases from grayscale, the lowest. M mode is a little bit higher, and even though M mode is grayscale, it's a little bit higher because you're scanning, and then you take that one line, and you scan, and then that one line, you scan that one line. So along that one line of information, that M mode line, in that particular spot, the spatial peak temporal average, or the TIS goes up a little bit. Color Doppler, even higher. Spectral Doppler, within that little, nope, once again, with a whole line of information, whether it's inside of the box or not, that whole line is a pulse line, and that's a Doppler pulse line, so it's far more strength than M mode itself. So that's thermal mechanisms, or how we measure thermal mechanisms. Then we have cavitation. Let me start with my little boat. I know I've mentioned this before, but I just think it's so cool in a weird way. Here's my boat. The propeller, the prop is completely underwater, and you've all seen off the back of a boat, whether you've ever been on a boat or not, you've seen the videos. It's just white, right? Just the water turns white. Well, that's because of a tremendous amount of bubbles formed. Well, those bubbles aren't from the exhaust of the engine or anything. That exhaust, like in this particular engine, the exhaust is going out that way. These bubbles are created inside the water. It's Bernoulli's effect. The high velocity of water suddenly reduces the pressure in gas that's in the water, just comes out of solution and creates bubbles. It creates bubbles from pure water. And then those bubbles go along. And so that's cavitation, and it's violent cavitation. Those bubbles aren't stable cavitation. It's actually called transient or inertial cavitation. And it is violent. On a very small area, it is very violent. So let's talk about this cavitation. Again, stable cavitation. Come on. Okay. Stable cavitation. Remember the bubbles. Now let's just say the bubbles already exist. It's very rare for ultrasound to have the strength to create a bubble when there wasn't one already. It's possible for very strong ultrasound to lower pressure to such a degree that a bubble is just simply formed out of solution. We don't usually do that though. So the bubble, let's say, it already exists, whether it's whether we injected it, bubble contrast, or whether it's for some reason we just have these little micro bubbles in between our cells. It's possible. Well, the wave goes by and they get a little bit smaller, and then they're normal size, and then they get a lot bigger, and then they go back to normal size, and then they get smaller and then bigger, and they just cycle through. It's stable cavitation. That's all well and good. It doesn't, in and of itself, stable cavitation, although it might create harmonics. Other than that, it doesn't really do much damage. Well, I shouldn't say that. It can do damage because there's fluids all around and in your cells. And if you think about this bubble that's getting much bigger and then small and then big and small, it actually is producing a mechanical effect on that water, and it actually get what's called microstreaming. So the H2O is suddenly flowing around. Let's say I'll send it this direction, and maybe some of it goes off in this direction, but water could actually, the interstitial, it's called interstitial. Ooh, okay. That was pretty bad. Interstitial fluid can get pushed around, and it can get pushed around. And now, once again, very small area, but just within this small area, the effects can be pretty grim. And now we have breakage of these cells. We could actually destroy some cells through microstreaming. Even if this happens in an adult, do we honestly care if 3 or 4 cells, maybe even 100 cells, have been damaged? Well, I guess we care, but we don't care that much. But on an embryo, it's a different story. So this is
Hey, Kurt.
Yes, sir.
Not to go into an extremely touchy subject, but I'm going to.
Okay.
Just so people understand, I am pro-life.
Right.
But since it can be done.
I've got my finger on the eject button. No, go ahead.
Since it can be done that way, especially since, you know, at the very beginning as a zygote, why not utilize ultrasound in that aspect for abortion? To disrupt the cells in such a way that the body would end up naturally aborting the child.
Right.
I mean, that goes into an ethical debate
you're not
and whatnot, but
yeah,
has it ever come up for them to talk in that medical terms?
Yeah, I mean, I've actually thought of that possibility too. And like, could this be used? I think one problem would be is that what if it only halfway worked? And so, the baby doesn't die, but it's now deformed, and you did it. So, but I agree. I mean, I've actually thought of that too. Like, is that something that they could do? Is actually.
Could it also be something that's less traumatizing? I mean, guys, I could also see how anything past, like the first 8 weeks, it wouldn't be viable to be able to do something like that.
Yeah, but, if the baby is literally that big, I think an argument, and I'm pretty much pro-life as well, but I think an argument could be made that, it wouldn't feel anything. It wouldn't know the difference. The baby wouldn't know the difference. But it's traumatizing. Maybe, but then again, what they do now is for an ectopic pregnancy, they give the patient methotrexate, which is a cancer drug. Well, cancer drugs specifically attack fast growing, fast dividing cells, which is why you lose your hair with cancer treatments. And an embryo is fast dividing, and so that would be, so they use methotrexate. But yeah, I mean, they probably could go to Russia. I'm sure they're already doing it.
Russia was the first to come out with PRK during the Cold War. They didn't want anybody wearing glasses in their infantry, so they might be doing something like that.
Yeah,
but anyway, back on topic. I'm sorry.
That's all right. So that's stable cavitation. Transient cavitation is even more unlikely with general ultrasound use. The chances of you popping bubbles is pretty low. But I suppose it's possible. I suppose it really depends on the bubble, I guess, the size of the bubble and everything to begin with. But so transient cavitation, if you raise your power, if you're going along and you're microstreaming and you're like, you know what, that's not enough. Let's raise the power and just pop all the bubbles. That can happen. Transient is also called inertial, is a more modern term, is inertial cavitation. But either way, transient cavitation or inertial cavitation. We've lowered the pressure. Remember, this happens in low pressure rarefaction of the beam, of the sound beam. The bubble gets so big that it pops. It does this violently on a very small microscopic level, but it's violent on a microscopic level. A little bit of light is formed. A pressure wave. Is formed, and heat. Now, once again, microscopic, but unbelievable heat, like approaching the surface of the sun, which is or like a lightning bolt type heat. Really unbelievable heat, but it only affects cells in the immediate vicinity. So this cell, these cells right here. So even though we're talking about incredible pressures and incredible heat, it's such a small amount to begin with that it's very, very localized, but also destructive. Your book says something about the destructive effects of transient cavitation are not considered clinically important since they are highly localized and affect few cells. Well, yeah, I can see they're not clinically important, but I thought it kind of, suggested that it was less destructive than microstreaming. No, this is definitely more destructive. There's a video I usually show of this of these shrimp, and yeah, what the hell, I'll find it and assign it just for the fun of it. You guys could watch it. These shrimp that hunt by by moving their claws so fast that they create a low pressure. Bubble is created out of nowhere, and it pops with such force that it actually stuns their prey. It's kind of cool. Okay, mechanical index. Yowza. Mechanical index, MI. It's another value you might see on the side of your screen. Oh, I can't remember what the general numbers are for mechanical index as well. I think they're like 1 as well. But the highest mechanical indexes are done with high peak or low, I guess, peak rarefactions. So the deeper it goes in the rarefaction, or the more that everything is stretched out in the rarefaction, the more mechanical index we have. In other words, the idea that we could create a cavitation bubble, and lower frequencies. So if you do want to cause cavitation, use low frequencies with very high power. Yeah, okay. The mathematics of MI have already been, we don't have to worry about the mathematics. Okay. Where do I think I'm lost on my screen here. Oh, that's right, here we go. Little all over the place with this one. Okay, so epidemiology, population studies, empirical. It is empirical. That is an exposure response method which utilizes clinical surveys. When the occurrence rate of bioeffects is small, the population studies require many subjects. So in other words, when the occurrence is small. So if you're only expecting a 0.2% increase in cancer because of ultrasound, let's say that's the empirical study. You know, you can't make that study with 20 patients. You're going to have to have more like 20,000 patients, and then you go back and you're able to look backwards and see, okay, all of these patients had at least 5 ultrasounds during their pregnancies and their offspring, their babies. Boy, it does seem like there's a slight increase in kidney cancer, and so that's that kind of study. But a large percent of it. Was not associated with it. So far, data has found that ultrasound exposure is not associated with fetal outcome, adverse outcome. Studies are also often retrospective. You'd be surprised how hard it is to find someone looking back over their shoulder without it being like creepy. So I found a Chihuahua looking over its shoulder. It's the only retrospective picture I could find. The information is obtained from old medical records. So you just go through records that already are in existence and you put them through a computer and do data analysis. Problems is ambiguities may exist in the data, such as, well, gestational age, number of scans, technique, exposure time. You might have some techs who spend an hour looking at your baby. You have other techs who spend 5 minutes. You have some people are a lot heavier. A lot of moms are very heavy. If they're very heavy, then the exposure to the baby is probably less because the baby's farther away versus a skinny mini. How many exams did you have during your pregnancy? Those are all ambiguities. Those are limitations of a retrospective study. Prospective studies looking forward. Oh, I've got, that was a, yeah, there we go. Looking forward. And he's looking over at that group of people, and he's going to do a prospective study. Protocols established and specific information systematically obtained. So prospective studies are interesting to be in. If you ever work for a university hospital or something like that, you might be involved in a study where you will see 200 ultrasound patients, 200 OB patients, let's say, and you do the same exact thing with every single patient, being very careful to do the same thing. That way you're creating the same type of standards for every patient. And then we could better understand this is okay. Every time they did this, 10% of the time we found this on the patient. So a lot of times we'll do that with new techniques on looking at the fetal heart. And this is okay. We want every single, we want this ultrasound tech and maybe 2 ultrasound techs who are specially trained to look at the heart. And we're going to look at the heart from a new angle. We're going to do that for 200 patients. Each tech does 200 patients. And then we're going to look at the results and what was the success rate? Is this a useful picture? So that'd be like a prospective study, which are nice. Randomized studies is just basically saying 100 patients are going to be seen, looking at the heart in a certain way, and another 100 patients are going to be seen looking at the heart, however, whatever way they're currently doing it. And by doing a randomized, am I saying that right? Yeah, more or less. The book says one group is exposed to ultrasound, the other is not, but I guess considering we're talking about FDA type stuff, that'd probably be better. You look at one group who is exposed to ultrasound, what kind of problems do they have or don't have? Then you I don't know, go to a rural country where they don't have ultrasound and you look at them and tell. But then again, with that situation, you have a lot of other mitigating factors. Clinical safety and prudent use. I feel like we've already talked about that. Training and research. We talked about that. Electrical safety, guys, is something. Some of you will end up working in locations where they haven't updated their machines in a while. That's always a challenge. But you could still, even the older machines, you could still see a lot. You just have to work at it a little harder. But if you see frayed
Would an electrical tape just help with that?
it will help, but that's a short-term solution, and you should be putting your foot down.
I have worked
The voltage
in clinics,
yeah,
with equipment, X-ray equipment that was 50 years old,
yeah,
constantly breaking down. And instead of buying new equipment, they'd spend the money over the course of a month that would have bought a brand new machine that would have been digital.
yeah. Yeah, radiology
It's
managers
like,
are
why do
idiots.
you do that when if you just spend the, and yet they still do this with ultrasound as well? I don't get it.
It's expensive.
But what's more costly in the long run? Dropping the money to begin with or the upkeep?
Well, yeah, I mean, you're thinking logically. You have to think like a radiology manager, which is not necessarily logically.
You know, they think more like a military manager.
Yeah, I've never been in the military, but sounds about
If it
right to
makes
me.
sense, it's not sensible.
So I'll take this opportunity to. This is a wheel. And this is a no-no. So just, yeah, if you see frayed wires, bring it to someone's attention and just say, look, there's a lot of voltage. There might not be a lot of voltage coming back, but there's a lot of voltage going in, and that could sting. Honestly, it's probably not going to kill you, but it could hurt, you know. So, and this is not something you should be fooling with. And having said that, it's a good time just to say these cords should never touch the ground. Also, you know, a lot of people, they'll take the cord and I can't reach they'll wrap it around their neck. Yeah, okay, except that cord's been dragged across the hospital floor and I don't know, Ebola. I don't know what they've got. You know, there's always something on the floor you don't want to catch. So that's not
There's MRSA in every hospital.
Yeah, MRSA is for sure, and C. diff and that kind of stuff. So those cords, especially because they're so important, there's hundreds of tiny little wires running through them. We don't want to crack any of those. The electrical out, the power cord, the data cord, keep all of that stuff up and out of the way. You'll notice in our lab, I wrapped all the cords in that tubing because we were running over them. You know, it just fried me, it bothered me. So be careful with that. And then it ends with Alara, as low as reasonably achievable. Just know that in general. I do not know why I have a script here. I think it was when I talked about this alone, recording with myself here, I didn't, I put that script in there for some reason, and I can't remember why. Hmm. Is there another page? No. Okay, well, let's any questions on this chapter? I want you guys to read through the whole chapter. Read through the statements in here as well from the AIUM. That's fair game for a SPI, but I think it leads to a rather boring class if I go through all of that. So let me